Hello, this talk is titled Dibs, Database Isolation by Scheduling. I'm Kevin Gaffney, and additional authors of this work are Robert Claus and Jignesh Patel. Conventional database systems can often be broken down into smaller components that interact with each other via well-defined APIs. However, one of the truly monolithic components of a database system is the transactional storage manager. The transactional storage manager is responsible for providing the properties of atomicity, consistency, isolation, and durability. While we normally think of each of these properties as a separate entity, the components that provide these guarantees are often deeply intertwined. This interdependence between components may lead to large and complex code. From a system design standpoint, this complexity is undesirable for two reasons. First, the substantial development effort required to implement a transactional storage manager may discourage system implementers from adding support for transactions. For example, transactions were initially unsupported in early versions of RocksDB, and MongoDB used a global database lock to serialize operations prior to its 2.2 release. Second, the complexity may lead to bugs and unexpected behavior. For example, recently, the transaction isolation checker L found a violation of serializability in PostgreSQL 12.3. For certain workloads on MySQL, switching from read uncommitted to serializable isolation increases performance. For these reasons, we were interested in reducing the complexity of the transactional storage manager by extracting parts of its functionality into independent services. In this project, we focus on a modular transaction isolation service, which we call Dibs, or Database Isolation by Scheduling. In the remainder of this talk, I will discuss how we optimize predicate locking for high throughput and how we combine our optimizations into a modular transaction scheduler. Then I will present an evaluation and a few use cases, followed by a discussion. At the core of our approach is predicate locking, an old technique that was originally proposed as a solution to the phantom read problem. But we focus on an additional benefit of predicate locking, its independence from the contents and implementation of the database system. A predicate lock is defined as a tuple RPA, where R is a relation, P is a predicate that can be evaluated on some tuple T in R, and A is the access mode, which is either read or write. Two predicate locks are said to conflict if they access the same relation, at least one is a write, and there exists some feasible tuple in the relation such that the conjunction of the two predicates on that tuple evaluates to true. The first two conditions are relatively easy to verify. However, verifying the conjunction reduces to Boolean satisfiability, which is NP-complete. Typically, this is achieved by converting the conjunction to disjunctive normal form, or DNF, but for certain forms of predicates, this requires exponential time and space. Furthermore, a new predicate lock must be compared to every other predicate lock to determine whether it conflicts, which requires synchronization between threads. I will now discuss our optimizations that reduce the overhead of predicate locking. Our first optimization, conjunct grouping, reduces the exponential blowup of converting to DNF. Observe that each term of a DNF predicate must contain at least two references to the same column to be a contradiction. For example, A equals V1 and A equals V2 is a contradiction if V1 does not equal V2. However, A equals V1 and B equals V2 is satisfiable for all V1 and V2. Conjunct grouping first separates the conjuncts of two predicates into groups that access disjoint sets of columns. Then we convert each group to DNF individually. The overall predicates conflict if any of the groups are satisfiable. In this example, converting to DNF results in a disjunction with 16 terms. By first applying the conjunct grouping, we only need to consider two disjunctions, each with 4 terms. Our second optimization, prepared predicates, reduces the latency of checking for conflict. Applications commonly use prepared statements to reduce overhead of parsing and optimization and to protect against SQL injection. In a similar way, parameterized predicates can be analyzed offline, reducing online overhead. To this end, we define a conflict graph that includes one vertex for each parameterized predicate. At each edge, we store a conflict predicate that evaluates to true if the predicates conflict. These example predicates conflict only if V1 equals V3 and V2 is less than V4. To solve satisfiability online, we only need to look at the edges of the given predicate vertex and plug in the arguments provided at runtime. Our third optimization, column filtering, reduces contention for a centralized set of predicate locks. Access to the centralized set of predicate locks must be synchronized among threads, which presents a severe scalability bottleneck. Instead of a single set, we construct some number n buckets of active predicate locks. We then define a function that maps each predicate's values to a subset of the buckets, ensuring that predicates that could potentially conflict are mapped to a common bucket. For example, some function on column A could map these predicates to different buckets, eliminating the need to compare them. However, predicates that cannot be mapped must be inserted into each bucket. I'll now discuss how we combine these predicate locking optimizations into Dibs, our modular transaction scheduler. Dibs is structured as a layer between a target data platform and its client applications. Dibs provides base functions that can be implemented to support various data platforms and client applications. Dibs contains a set of worker threads that continuously pull the client connectors for new transactions, acquire and release predicate locks accordingly, and pass on the transactions to the data platform. The predicate lock manager handles all the predicate locking and implements the optimizations we discussed earlier. We combine our optimizations as follows. First, for some predicate P, we determine whether P can be mapped with a column filtering function. If so, we only insert P into the mapped buckets, otherwise we insert P into all buckets. We then evaluate P against all other predicates in the buckets. If both predicates are prepared predicates, we evaluate using the conflict predicate described earlier. Otherwise, we use conjunct grouping to evaluate ad hoc predicates. I'll now present our evaluation of Dibs alongside some use cases. The workloads we use in this evaluation are TATP with 1 million records, YCSB with 1 million records and varying write intensity, and subscriber scan, which is a benchmark we developed to test the exponential blowup of converting predicates to DNF. Subscriber scan involves complex conjunctive normal form predicates, which are the worst case for converting to DNF, and we vary the number of conjuncts from 1 to 8. Our first use case is providing isolation as a service for new data processing systems. Here we evaluate Dibs as the sole isolation mechanism for a prototype system built on Apache Arrow. The system relies on internal data structures to provide consistency and does not provide atomicity and durability. It relies solely on Dibs to provide isolation. In this environment, we evaluate the performance impact of cumulatively adding each predicate locking optimization. For TATP, column filtering allows the system to scale up to 10 million transactions per second. Here, contention for the centralized set of predicate locks is the bottleneck, so the other optimizations do not provide noticeable improvement over naive predicate locking. For subscriber scan, with 20 worker threads and varying number of conjuncts per predicate, naive predicate locking performance begins to degrade beyond about 4 conjuncts per predicate, but our optimized predicate locking avoids this performance degradation. Our second use case is transaction merging to reduce costly writes to stable storage. A typical transaction processing thread looks like the following. After executing each statement in a transaction, the thread commits the transaction, which typically involves flushing parts of the transaction log to stable storage to make the transaction durable. Transaction merging adds an outer loop over multiple transactions, delaying the commit until the statements of multiple transactions have been executed by the data platform. The problem then becomes that the transactions within the same outer loop are not isolated. Here, we can add a call to Dibs to ensure that the transactions are now isolated while reducing the number of commit calls per transaction. This is analogous to group commit, but it is different in that it can be implemented as an independent layer rather than in the buffer manager. We evaluate transaction merging for TATP on SQLite 3. Transaction merging substantially reduces the number of fdatasync calls per transaction, which ends up resulting in a 3x improvement in throughput. Our third use case is column granularity locking. Recall that before we said 2 predicate locks conflict if they access the same relation and at least one is a write. If we modify that definition slightly to assert that 2 predicate locks conflict if their intersecting columns are not read-only, we achieve a finer granularity of locking. We evaluate column granularity locking in MySQL with 3 configurations. Integrated serializable, which is just MySQL serializable without Dibs, read uncommitted, which is MySQL read uncommitted without Dibs, and Dibs serializable, which is MySQL set to read uncommitted but with Dibs, resulting in serializable isolation. For YCSB and MySQL, we observe that column granularity locking provides a 1.4x improvement over serializable under high contention and comes close to the performance of read uncommitted. I will now conclude with a brief discussion of trade-offs. The main advantage of Dibs is modularity. We did not design Dibs to outperform highly specialized transaction processing systems, but to be a modular service that provides isolation with relatively good performance. This lowers the barrier to provide transactional support for new systems and decreases code complexity. The main disadvantage of Dibs is the pessimistic nature of predicate locking. 2 predicate locks may conflict even if there is no tuple in the database that satisfies both. For many transactional workloads, however, this is not an issue. I'd like to acknowledge Semiconductor Research Corporation for their support of this work. Thank you.